back. Let me quickly recall what we did yesterday. So we were trying to prove Mantle's theorem. Okay, we prove it, but in the proof that I presented, there was this one magic moment when I used some inequality, right? And then we were trying to figure out why this inequality, and we transform proof of Mantle's theorem into instance of a semi-definite programming so that I can just press button on a computer and get the solution. So what exactly we obtained is that the solution of Mantle's theorem is just obtained by bounding the following expression. Zero, zero. Was it like that? Richard, please check, because I was not taking notes during the lecture. We had something like this? Okay. Yeah, so we transform proof of Mantle's theorem into upper bounding this expression over some positive semi-definite matrix Q. And we used semi-definite programming where there was some unknown positive semi-definite matrix X with X0 in the top left corner, then those values for every graph, and then these matrix Q. Yeah, it was something like this. And the assumptions of the semi-definite programming was translated into the form. I'm just writing down what we had last time. If I'm writing something differently than it was, please correct me. Like this? Okay. So we run this semi-definite programming. This is a numerical procedure. So the computer is counting here, and after a few seconds, is giving us the metric. Yeah, the best metrics you can find, which will upper bound this. The upper bound here is 0, here. So I run it, and the computer returned the following metrics. As X0, we found 5 and then 8 zeros. Then similarly, found numerical values for others. It's looking like this. So these are X0 and the values of X1, X2, X3. And as a metric, found something this one. Well, you can imagine what's going on. This is what computer gave me. What it means, he found numerically best metrics, and he was able to prove Mantel's theorem, but not with half, but with half plus 8 times 10 minus 9 or 10. Yeah? Is it satisfactory for us? Like, no, we don't want to have a proof that Mantel's theorem works with not with half, but with half plus some small error. Yeah, so we are left with the problem of writing this matrix that the computer found in a more rational way, right? So that we have exact proof. So exact way. We want to have bound half, not a bit worse, and want to have exact metrics. We can check that it's really positive semi-definite, not that it's changed by some smaller epsilon, and maybe it has some small negative eigenvalue. Yep. Okay. So now the question is how to rationalize the output of this numerical method in order to obtain, firstly, a valid proof, and secondly, the proof that gives us exactly the bound that we want. Okay, so what could be the naive approach? So here you can guess, right? That this should be half, this should be 0, this should be 1/3, etc. And this should be nice metrics. Here the nice metrics should be half minus half minus half and half. And this was exactly the matrix I used in my proof. Yeah, like we were using in the proof of Mantel this vector. Formally, I had -1, -1, 1. The vector, right? Average. But then I was adding this inequality with coefficient half to what I observed. So basically moving this half here, I have exactly this matrix. Yeah, so this is explaining why I was using exactly this matrix. So if the problem is small, like here, you can guess the matrix, right? But imagine that you are solving a huge conjecture using lots of graphs, using lots of matrices. You have like matrix, I don't know, 1,000 times 1,000. You will not guess all the entries. You will be trying even to rationalize it just by guessing. So what you can do, you can, for example, fix some denominator and just round up every element of this matrix to this denominator. Okay? But what it can happen, there can be two things that can break down our proof. First, if I round up, I can round up this to exactly this number. Yeah, so half plus some small error. And this way, I'm not proving Mantel's theorem, I'm proving Mantel's theorem with an error. So this is not what we want. The second thing can happen is that if I round up metric to the closest rationals with some bounded denominator, I can obtain a matrix which is not positive semi-definite, and then the whole proof is not valid. Yeah, because I cannot say that this is at least 0 for every placement activity. Okay, so now what I want to do in the next, say, half an hour, I want to convince you that we can make those steps in an automatic way so that we will not lose in those two places. Okay, so first let's solve the first problem of getting the exact path. Maybe I will move up. So we are proving Mantel's theorem, so we know what we want to achieve, right? We want to achieve bound half, which means that here I want to obtain x0 equals half. So in this system of linear equations that are assumed in my program, I would like to have x0 equals half everywhere. So instead of putting this to the matrix and searching for it, I can just assume that x0 is half. And if I do it, assuming x0 is half, and if I do it, then the proof basically trying to prove exactly half, not trying to bound by the smallest possible number, but really trying to fix half. So, in other words, I found this matrix numerically, and I want, like, this matrix should satisfy this system of linear equations, but I want to satisfy it with half here. Okay. Second thing is that we are proving Mandel's theorem, and we know what's the extremal construction. Extremal construction that we expect is complete bipartite graph, balanced. Right? So when I was using in my proof, you recall there was something like this. And I bounded by longstanding. Yeah, there was such a part in the proof. In the extremal construction, I should have here equality. Okay. So what it means that the coefficient standing by those graphs that appear in my extremal construction should be tight. Yeah, here I found 1/6 by just half. It was not tight, but it's fine because this graph does not appear in my construction. Yeah. If I use a bound here, which is enlarging the coefficient by cherry, it cannot be tight for a complete bipartite graph, right? So if I'm expecting that this is my extremal construction, the coefficient by all graphs that appear there should be with equality. So in other words, if we move back here, those x1, x2, etc., those are exactly the numbers which are finding the difference between what I get there on the right and what I get to the left. So x1 is the difference between the coefficient here and the coefficient here. Yeah, x2 is the difference between coefficients here. In particular, from this numerically found matrix, you can see that x1, so this is for the cherry, and this is for the independent set of size 3. They are almost zeros, yeah, because we expect that it's tight for the extremal construction. While for this, I have something positive. This does not appear in my extremal construction. I don't need to have equality for this. Okay, so what's the conclusion? The conclusion is that whenever some graph appears in the extremal construction, like those two, then I should have, respecting x's, respecting x's should be 0. Yep. So the metrics that I'm looking for should satisfy also this. Yeah, I hope I haven't lost you. So if we expect what's the bound that we are trying to prove and what's the extremal construction, then we get this information from the extremal construction. Okay, and this way, the system of qualities that our matrix needs to satisfy can be written in a shorter form. We write it. So from the first one, what I get? Let me move half there. So it's -1/6. Let's check if I'm doing correctly. It's half minus 2/3, right? Okay, from the second equality, I just have x this equals 1/6. And the last one will be just. Yeah, you agree? But if I use this assumption, then the system of qualities that my matrix needs to satisfy comes to this. Okay. So now what we can do is just to solve this system of inequalities using values which are close to the numerical values found by the computer. Yes, so what could be the solution? Okay. So here, let me write it all. I need to use half as x0. I need to use 0 here and 0 here. This it needs to be something close to 1/3. Here I need to have half. Yeah. And now, if you use this half. So let me say, for example, that I have in the matrix Q, I need to have something which is close to half. Let me put it half plus 2 times epsilon. This epsilon can be negative, right? Just that it needs to be something small, something close to half. And then I can check what's happening here in those inequalities. So if I put half plus 2 epsilon here and calculate this coefficient, it will appear that it needs to be minus half minus epsilon, and the same here. And then from this equality, I get that this is 1/3 plus 2/3 epsilon. Okay. So in other words, if I use this metric for any epsilon, which is very small, I'm close to the matrix found by the computer, but now my proof is valid. I mean, it's really giving half as upper bound for the edge density, and it's tight in the extremal construction. I'm not losing anything by density of cherries and density of independence of S3. Okay, so this way I solve the first problem. So I will not obtain half plus some small error term, but I'm really using such a matrix obtaining half. Okay, the second problem was that if I round it, use some epsilon, I may end up with something with the matrix here, which is not positive symmetry. In this case, we can even calculate the determinant. You calculate the determinant of this matrix. You will see that this is exactly minus epsilon squared, which shows that if I round it with any error, like any, with epsilon like minus 10 to minus 12, whatever. If I do a tiny mistake, then immediately I'm getting a matrix which is not positive definite, right? If determinant is negative, it means that there is a negative eigenvalue. So my proof will not be valid anymore. Yeah, the problem is that the matrix that I need to use for epsilon equals 0. Yeah, this is the matrix I should use. The matrix has 2 eigenvalues. So eigenvalues of this matrix are 0 and 2. And now any tiny perturbation, so putting any epsilon, makes this 0 eigenvalue to be negative. I'm destroying my whole proof. Okay, and now how to deal with this problem? So the ideal solution would be somehow determine what is the space of the subspace which is generated by those zero eigenvalues. So let me say that I will call by zero eigenvector just eigenvector of this matrix for eigenvalue 0. Okay, so this matrix has two eigenvectors. One is for this eigenvalue, one is for this eigenvalue, and this one I call zero eigenvector. In general, huge matrix, there can be many those zero eigenvectors. And what I do, I take a space, should have more space here to erase. So I take a space, we call it here. It's a space generated, subspace generated by those zero eigenvectors. Yeah, so here I have like n times n matrix. Say that I have k zero eigenvectors. So this is k times n. So I have k vectors, each of size n, generated by those zero eigenvectors. And what I can do now, I can calculate its orthogonal complement. What it means, so you have the space of n generated by n eigenvectors, right? So some of them are for zero eigenvalue, so they are generating some space. And I look at the orthogonal space. Okay, so this is the orthogonal space, n minus k times n. And what I can do, I can write my matrix Q in the following form. So I take this orthogonal complement, transpose, multiply by some reduced matrix, and back by my matrix. So Q is some reduced matrix size n minus k times n minus k. So think about it. We have this n-dimensional space generated by eigenvectors of my matrix Q. I somehow found zero eigenvectors. Yeah, they are generating some space. And now the whole space somehow divide into two parts, like this space generated by zero eigenvectors and the orthogonal space. So the orthogonal space is now determined by some reduced matrix. And if I do it correctly, I mean localize all zero eigenvectors, then this reduced matrix will be positive definite. It will have all eigenvalues strictly positive. Yeah, because I take out all zero eigenvectors. Okay, why I do it? Because if I now do this and then not round the matrix Q to the closest integers, but around this reduced matrix to the closest integers, okay, I'm changing the eigenvectors a bit, but since they were all strictly positive, and I'm changing just by a small, tiny value, then they are still positive. Okay, so I'm able to rationalize it, like make it from numerical values into some nice numbers, and then multiply by those vectors the orthogonal complement and obtain a matrix Q, which looks like this matrix, but it still keeps the 0 eigenvectors. It's just approximating those eigenvectors for positive eigenvalues. Okay, it seems hard when you first time hear about it. By the way, I think the lecture might be hard for you because we start with some analysis and probability, go through numerical analysis, and now I'm doing linear algebra. And it's supposed to be a graph theory lecture, but we will do some graphs later, don't worry. So let's see how it works on the Mantel theorem example. I want to keep this one space so it's easier for the online viewers. So let me erase a bit here. Okay. How to find this 0 eigenvectors? There is one more thing that we can take out from the extremal construction. Because what we are using this matrix Q for, we are using it in saying that this inequality is at least 0, right? So in general, that's some vector of densities times the unknown matrix Q, and then average is at least 0. This is what we're using in our proof, right? So in the extremal example, I need here equality. What it means that I have equality here, it means that the vector for which I'm using multiplying the matrix is 0 eigenvector, right? If I multiply the matrix Q by this vector, I obtain 0. Yeah. So in other words, those 0 eigenvectors that I need to find here, they're exactly the vectors that can appear in my extremal construction. So let's move back to my proof of Mantel theorem. So this is the extremal construction that we expect. The vector I'm using in our proof was this one, right? And now notice how it behaves in the extremal construction. Wherever I put the root, then the non-degree is just vertices in this path. Yeah, so it's half of the all vertices. While the degree is all the vertices. So if I'm using this inequality in the proof, and it's equality in the extremal construction, it means the vector half and half needs to be 0 eigenvector of my matrix. Yep, you understand? Because if I multiply it by my matrix Q, I need to obtain exactly 0. Okay, so now let's follow this pattern. I found the 0 eigenvector. Now I need to find orthogonal complement. Orthogonal complement, so I need to find, okay, now here I have 2 times 2 matrix. I have 1 vector, so the orthogonal complement is also just 1 vector. And it needs to be perpendicular to this vector. So an example, I can take, for example, 1 and -1. Yeah, it's orthogonal because if you compute the inner product, you get exactly half minus half, which is 0. Yeah, if the inner product is 0, it means that they are perpendicular. Okay, so I found the orthogonal complement. It's generated by single vector. And now I would like to write this matrix in this form. Okay, so now this Q tilde matrix, this reduced matrix, will be of size 1 by 1. Yep, from 2 times 2, I removed 1 vector, I have 1 by 1. So what I have, let's say that this 1 times 1 matrix is just consisting of a single value called Q. I multiply it by this vector from both sides. Yeah, so it's 1 minus 1, 1 minus 1. And if you multiply it, I should obtain my matrix Q. Okay, and after this multiplication, you can see that this is giving me exactly matrix of this form. Okay, so what's the lesson? It means that when I'm trying to prove Mantel's theorem, and I'm expecting that bipartite graph, balanced bipartite graph is extremal, then the matrix Q I'm using needs to be of this form. Okay, and we know that it's form half plus some epsilons, U minus half minus some epsilons. So immediately from this, we get that epsilons need to be 0. Yep. Okay, and it means that we have really this matrix, and this is exactly the matrix that I use in proof of Mantel's theorem. So in other words, everything that I said today and yesterday, you can plug into computer, right? You can program multiplication of flags, you can program averaging operator, you can program changing the problem that you want to prove, graph theory problem, into some kind of minimalization over semi-definite matrices, right? Then you can add to your program what you expect to be your extremal construction, which will make this approximation good. So it will assume that this is half, that it's the quality where we expect quality. You can calculate 0 eigenvectors, as I calculated here, generate the space, the orthogonal complement, and find this reduced matrix, and then round the reduced matrix to the closest integers without making any errors, 2 big errors. And at the end, you obtain matrix Q, which will be positive semi-definite, right? Because I approximated only positive eigenvalues, so they are still positive if I haven't made 2 big rounding mistakes. And I keep the 0 eigenvalues. Yes, so at the end, I obtain a formal and valid proof, which is giving me exactly what I want. Are there some questions? In general, now you can imagine that you want to prove some huge conjecture on some big number of vertices, like not necessarily like here, just triangle and edge, but really something bigger. Then all the steps can be automatized, right? Everything I can do, I end up with some huge matrix, 1000 by 1000, for example. I find the 0 eigenvectors. Here, after finding 0 eigenvectors, I got exactly one matrix. I need to have exactly that this is Q equals half. But in general, it's not a unique matrix. Still, there is lots of freedom, but I can round it the closest integers, keeping the system of equalities that I assume, and then it will give me exact proof. So the nice thing is that you don't need to write this whole program by yourself because somebody else wrote it already. So there is a program Phlegmatic. It's an open software available on GitHub. I'm not writing the exact address. If you search for it online, you will find it. And this software basically contains everything that I teach you today and yesterday, and doing all those steps in an automatized way. So what I want to do now is I want to show you how to use this software so that if you're even not experienced in programming, you will be able to solve graph theory problems just by writing a few lines in this program. So the program was written by Emil Von as a joint project with Viktor Falkasz-Rawry. And now it's developed further by Jakub Sijachan. It may contain some bugs, but usually Jakub is responding quickly and repairing if you find a mistake. Okay, so how to prove mantle, for example, in Phlegmatic. So firstly, I'm defining what's my problem. So I'm writing the program that my problem is a graph problem. Phlegmatic can do flags not only on graphs, but also on oriented graphs or directed graphs, and also on 3 uniform hypergraphs. Yeah, so at the beginning, I'm just providing that I'm doing graph problem. And parameters of my graph problems are the following. I want to use densities of graphs on 3 vertices, right? This is the small n. 3 vertex graph that I used in my proof. Then I'm writing what I want to maximize. So I want to maximize density of edges. So I just write density and then what I want to maximize. And here I should provide a graph that I'm maximizing. And the graphs in Phlegmatic are provided in the following way. Firstly, you put how many vertices your graph has. And then you provide edges. And edges are provided just by writing numbers where your graph has always vertices numbered by consecutive integers starting from 1. Yeah, so for example, edge that I want to maximize here is just containing 1, 2. So I'll just write this. Yeah, so this is exactly graph, which is consisting of 2 vertices connected by an edge. Okay, I need to also write to the program that I'm forbidding triangles. Yeah, so I'm adding assumption, forbid, and then writing triangles. So triangle has 3 vertices, 3, and then I need to provide all the edges that are there. So 1, 2, 2, 3, and 1, 3. Yep, this is the triangle written in the language that Phlegmatic is using. Okay, so this is defining the problem that I want to solve. Then I can ask Phlegmatic to solve it. Okay, so this line is just doing the numerical calculations. So it's writing the problem in this way, yeah, as minimizing some x0, which upper bounds all those, creating the metrics and doing the numerical calculations. Okay, so this step is solving the problem numerically. Okay, let's move back. Then I want to do the rounding. So I need to provide to my program what extremal construction I expect so that he can do the rounding procedure correctly. Yeah, we're using the extremal graph is complete bipartite in order to determine that the bound we are hunting for is half and what are the 0 eigenvectors. So in Phlegmatic, it's set extremal construction. And here I need to provide what's the extremal construction. Phlegmatic has some extremal constructions coded, for example, blowups of graphs, balanced blowups of graphs. So a complete bipartite graph, balanced complete bipartite graph that I want to provide here is just the blowup of an edge, right? So I put graph blowup construction. And of which graph it's a blowup, so it's a blowup of an edge. One. Okay. So this adding extremal construction to the problem is exactly what I was doing there. So calculating this x0, where for which xi's I need to have quality, and calculating the zero eigenvectors. Okay. So if I calculate this, I can make the rounding procedure. So in Phlegmatic, it's just by writing make exact. And this step will round the matrices, those reduced metrics, after keeping the zero eigenvectors, and then recalculate back to find the matrix Q, and we obtain a valid Q. Okay, so now proof of Mantel theorem is just writing those 4 lines in Phlegmatic, pressing enter, and after a few seconds, computer is generating a valid proof for us. Quick and easy. There are places here where you can do something more. For example, in this procedure, I can add additionally what size of denominators I would like to use in rounding procedure. If I don't provide anything, he's assuming some specific value. I can also set what kind of semi-definite programming solver I want to use. If I'm not providing anything, he's using CSDP. This is a very common semi-definite programming solver. I can also provide here what kinds of rooted flags he's using, or which matrices, for what types. So you can provide lots of additional things to your program. Okay, I think it's a good moment for a break. So let's make a break here. If something was not clear, you can ask me during the break. Thank you. Okay, I think we can resume. Solving Mantel theorem is easy, right? So if this would only solve easy problems, then it wouldn't be so interesting. So let's now solve harder problems. As Hongyu already mentioned yesterday, there was this Ertes pentagon conjecture that was open for 30 years. And now let's see how we can solve it using Phlegmatic. Okay, so the conjecture was to maximize the number of pentagons among graphs which do not contain triangles. Okay, so I define my problem in Phlegmatic as a graph problem. Now I would be working on 5 vertex flags. I want to maximize pentagons. Yes, pentagon is a 5 vertex graph with edges 1, 2, 2, 3, 3, 4, 4, 5, and 5, 1. Right? Then I want to forbid triangles. So it's as before, 1, 2, 2, 3, 3, 1. Okay, so this is my program. So I'm writing solve it numerically. Okay, now the Phlegmatic is doing calculations. After a few seconds, we have a numerical solution. So we set the extremal construction. And now the extremal construction, as suggested by Erdős, is a blow-up of a pentagon. So once again, graph blow-up construction. The pentagon. 1, 2, 3, 4, 5. Okay, so now Phlegmatic is calculating what's the density of 5 cycles in the construction, for which 5 vertex graphs appear there. So I need to have equality for those graphs, and what 0 eigenvalues I can have. So for what placements of my labeled graph, for every placement of the labeled graph, I obtain some vector, and this needs to be the 0 eigenvector. So after he calculates everything, I can ask him to round the matrices to make the solution exact. And now Phlegmatic is responding that, yeah, I proved the bound 24/625. These are the exact matrices that you should use. And this is solving Erdős conjecture. Yeah, you see the powerful of the method. Suddenly now, like 10 years ago, this was a conjecture, and now it's like 4 lines in a program and a few seconds, and the conjecture is solved. Yeah, so I hope this is showing you the powerful approach of flag algebras. Not only we are able to solve problems that we were not able to solve earlier, and we have nice language to write density constraints and things like that, but also it's completely automatized. Right? We can solve the problems without thinking. I just provided what the problem I have, what I expect to obtain, and computer gave me solution immediately. So after this, it was quite funny when somebody was proving some problem. I got it to review, and I said, oh, but if you write those 4 lines in the program, I get the same solution. So why proving it, right? Okay. During the break, I got this question. So let me answer maybe globally. What if we don't know the exact construction, or we know the exact construction, but it's not easy? For example, it's not the blow up of a graph, but something complicated, and we still want to use Phlegmatic. So what you can do, you can just provide to the program all the information that he needs from the extremal construction. So what's the bound that you are aiming for which graphs you expect equality, so which graphs are expected to appear in your extremal construction, and what are the 0 eigenvectors. So let's do some example. And by the way, I will show you an example which not only works on graphs, but oriented graphs to have some diversity. So let me consider the following problem. Problem is to maximize the density of induced stars of this type. Yeah, I induced means there is no edge here. Okay. So imagine that you have such a problem. For every oriented graph, I allow between every 2 vertices an edge directed in one of the graphs. And I would like to maximize the number of those. If I give you several minutes to think about it, you will come up with an idea of dividing your graph into 2 parts and putting all edges directed one way, with this part being independent sides. Okay, if I do it like this, then whenever I pick one vertex from this part and 2 vertices from this part, I have the chariot, right? But now, inside this part, I can put whatever I want, and I will not destroy those cherries. So what I do, I repeat this procedure. I put here a set, I divide this into two sets, and put all the edges directed one way. Yeah. Here inside, I don't put any edges, keep it as independent set. But on this side, I can continue. I can iterate. And I can do it as long as I can, as I wish. And this was conjectured to be the best example and was proved by Victor Falkers, Rafri, and Emil Von, so the authors of the phlegmatic software. Later, it was even generalized to all stars, like one vertex and outgoing edges, like one, and then by O, Ma, Norin, and Vu to any variable stars. So we can have some edges going in and some edges going out. Okay, so what could be the solution here? What we expect? Okay, this is the construction we expect, but of course, it does not seem correct to make it balanced, right? Why we should keep it balanced? So let's say that this is of size some x, and this is of size 1 minus x. I mean size, relative size. Yeah, and this will be continued. So now we calculate this density of those graphs. I need to pick two vertices from here and one vertex from here. Which appears with this probability, right? So it's 1 over x times n choose 2 times x times n. But this, the density will be divided by n choose 3. So in the limit, it's just something like multiplying by 6, right? Okay, but this is on the first layer. It's only counting one vertex here and two vertices here. But I can repeat it in every other layer, right? Continue. So this is here, but if I put both three vertices into this part, then I get the same. So if I have all three in the same part, which happens with probability x cubed, I get the same value. And I continue. If all of them are in the next layer, the third layer, this will happen for the x to the 6th power, and gives me the same power. And I continue. Okay? So my final density would be something like this. This would be 1. Okay? So now what I can do, I can maximize this over all x and 0, 1. We calculate what x will give me the best bound, so the best value. Okay, if you're not mistaken, this is for optimize for x equals square root of 3 minus 1 over 2. And then the maximum will be 2 times square root of 3 minus 3. Okay, so what's the problem now? Firstly, this is irrational. So definitely, if you want to obtain a solution which is not rational, we will not be approximating our matrices to the closest rational number, right? Because definitely we will not obtain a correct solution. So we need to be more clever. So what we'll be doing, we'll be working basically in the field, which is not rationals, but it's rationals extended with square root of 3, or better, rationals extended with this x, right? So it will be easy. Okay. So let's try to solve it in phlegmatic. I define my problem. So it is problem on oriented graph problem. I work on graphs on 3 vertices, and I want to maximize density of a 3 vertex graphs which contains edges 1, 2, and 3. Yep, this is my problem. I don't forbid anything. I just want to maximize. Okay. This can be done easily. I can solve the problem numerically. Okay, so I obtain the numerical metrics. But now comes the harder part: how to make it exact in this with the strange values and the strange construction that I cannot provide. So firstly, I will write what it means that I want to work in the extended field. In pragmatic intuition Sage, you can define it by the following code. I define my X. This is basically meaning that I want to work in rationals extended by some X. And this is defining my field as a number field. Extended by X, which is this number, and I provide this number by just writing the minimal polynomial, generative polynomial. So in this case, it's just this. And this has 2 solutions, so I write which one needs to be close to 1/3. Okay, so this doesn't matter how it's written exactly. This is just defining that I want to work in the rationals extended to this square root of 3 minus 1 over 2. Okay, and now the important parts for our problem. I want to set the extremal construction. As an extremal construction, I'm writing that I'm working in the field defined here, not in rationals, or it is on default. And I just write what's the target bound. Yeah, this is fixing this x0 in my rounding procedure. So here, if x is this number, then the target bound can calculate it as 4x gives me 2 times square root of 3 minus 2 minus 1. So my target bound is 4x minus 1. Formal speaking, I use multiplication. So this line is basically saying that we work in this field and 4x minus 1 is the target bound. So this needs to be used as the x0. Okay, is it clear? Good. The next thing I need to use in my rounding procedure was which graphs appeared in the extremal construction, right? To see which those x1, x2, x3, for which one I need to have exact bounds. So this in pragmatic, it's written by or graph. And I just enumerate which graphs appeared in this construction. Okay? For example, if you look at directed triangle, the directed triangle does not appear anywhere. Yeah, so for directed triangle, it not necessarily needs to be tied to the value for directed triangle in this expression. So I can enumerate, and just by checking, saying that those four graphs appear in this extremal construction. So for them, I need to have exact bound. Okay, and the last thing I used in the rounding procedure were the zero eigenvectors, right? I need to provide zero eigenvectors. So this can be counted from our extremal construction, conjecture extremal construction. I work on a 3 vertex graphs. My labeled graph is just a single root. Yeah, and the vector of densities is non-edge, edge going out, and edge going in. Yeah, this is the vector that we are working on. Okay, and now wherever let's say I place the root firstly here, and I calculate what's the vector I can see. So non-edges, like vertices that are not connected with my root, this is exactly this. Yeah, it's of size 1 minus x. Edges going out from this guy, there are none, so 0. And edges going in, this is the whole set. So vector 1 minus x, 0, and x needs to be a 0 eigenvector in the rounding procedure. Okay, but this is not the unique one. There are more. For example, if I take not this vertex, but vector here in the second layer, what I can see as non-vertices which are not connected is exactly this set. Yeah, and this set is of size x times 1 minus x. Edges going out, there are exactly here, so it's 1 minus x, while edges going in is this set, which is x squared. Yeah, so it's the second vector, which needs to be a 0 eigenvector in my rounding procedure. So I want to add those two vectors here. And that's my problem. I add 0 eigenvector and okay, this 0 means that for which labeled graph I'm adding. Yeah, I have just a single labeled graph. It's a single vertex. Its number is 0. If I had more labeled graphs, I would be adding for the one labeled 0, the one labeled 1, etc. Yeah, so I'm adding to this, and I'm just adding two vectors, so it's forming a matrix in field K with two vectors. One is 1 minus x, 0, x. Let me check if I write it. Yes. And the other one, x, 1 minus x, 1 minus x, x times x. Okay. And then, no. Yes. So this line is adding those two eigenvectors that I expect to be 0 eigenvectors because I expect that this is the extremal construction. Yep. Okay. So I provided to my program everything that I expect to be there, right? Now I can do the rounding procedure. So asking for, I ask the program to make it x. And now if you run those 8 lines, it's solving the problem. And providing that indeed the best bound we can have is 2 square root of 3 minus 3. So what I want to emphasize that we obtain a solution in not rational field, right? So we are able to solve problems even if the extremal bound is some strange number. Are there some questions? Yeah, in general, if you have a problem and you expect some construction, or you can expect even few constructions, right? You imagine that you have a problem. For example, Goodman bound is to minimize this, show that this is at least quarter. Yeah, it has many extremal constructions. For example, complete bipartite graph satisfies it, but also random graph satisfies it. And each such graph has different vector that should be zero eigenvectors. Yeah, so what I can do, I can just provide phlegmatic all vectors coming from all the constructions I know, and it will help in doing the random process, the rounding procedure correct. Some questions? Yeah, so if we don't know extremal construction at all, then what can happen is that when we will be rounding, we'll lose something here, or our matrix becomes not positive definite. Okay, so let me answer two ways. First, you may be interested not in solving, like obtaining exact bound half, but you may be interested just in obtaining some bound, right? Not necessarily tight. So what you can do, you may not set any target bound and just ask phlegmatic to round the problem to the nearest rationals, but keeping the matrix positive semi-definite. So it will lose something here, will obtain a bit worse bound, but the proof will be valid. Yeah, so sometimes there are some problems that we would like to obtain as good bound as possible, but not necessarily tight. Yeah, so we can do it here without knowing any extremal construction or anything. Yeah, just by asking, keep the problem semi-definite and don't care about the bound. It also can happen that you have a problem, you don't know the extremal construction, you use this flag algebras approach, and it occurred that it's stopping on something which is specific densities of graphs. And from this, you can try to guess. Yeah? For example, here, imagine that we don't know that complete bipartite graph is maximizer in Mantle's theorem. But from here, since this is not zero, you would expect that, okay, so your extremal construction that I don't know how it looks like should have zero density of those. Okay, so you can guess that, oh, it should be complete multipartite. Oh, but it's triangle free, so it needs to be bipartite graph. And then you look at this and you see, it seems that I get that half-half, or half plus epsilon, half plus epsilon, something close to half, is zero eigenvector. So it means that if I put this vector in my unknown construction, I should be close to half and half, wherever I put the vector. Oh, so this bipartite graph should be probably balanced. Yeah, so what I want to say is sometimes you don't know what's the construction, you try to solve the problem, and suddenly the program is suggesting you what could be your construction and what you will try to prove. Yep. So based on this, you can guess what's your extremal construction provided and obtain an exact bound. Okay, our time is running out. Do you want to finish earlier or see one more application? Hard choice. Erase something in the meantime. So one more application, or we finish a bit earlier? I need at least one answer. Okay, with voting ending 2-0, we'll do one more application. So let me solve some problem, but not on graphs, but on oriented graphs, to make something to show you that Slax works not only in graphs, but also in other settings. So during the lecture, I explained how to multiply graphs, how to do averaging, etc. And I was doing all the time on graphs. But you can imagine that on oriented graphs or other structures, basically everything looks the same. Yeah, so let's say that I work on oriented graphs and I have oriented outgoing edge, and I want to multiply by oriented outgoing edge. Yeah, so what it can be, I have two random vertices. I need to have two edges going out from my root, but between I can have this or this. Yep. If I have this multiplication, similarly, if I have two vertices here, I need to have at least one going out and at least one going in. And between, now I have many choices. I can have no edge. I can have edge going this way, so creating a directed triangle, but I can also have edge going this way. And now the coefficient is half everywhere because there is probability half. I will choose the edge going half. Yeah, you understand. So we were defining everything on graphs, but it's very easy generalizable to other structures using the same way. So the problem I would like to solve in the next remaining few minutes, consider the following: maximize number four cycles, directed force. And here I'm not talking about induced, but just 4 cycles. So I want to maximize this, but here it can be some whatever. I don't care. Okay? You understand the problem? So since I'm interested in just maximizing 4 cycles, I'm not forbidding any structure, then having a non-edge is useless, right? It's always better to add an edge. Maybe I will create some 4 cycles, but definitely I will not destroy anything. So I can say that this is internal. Yeah, because I can add those edges in places where C4 was missing, the edge was missing. Okay, and I want to prove that this is at most half. Why half? Because of the following construction. I put all the numbers. Yes. I put all the vertices on a circle. You connect every vertex with everything going right up to up and from left up to half, and just rotate it. Okay? You can calculate that densities of 4 cycles in this construction is half. Formally speaking, I have 2n+1 vertices and connect every vertex with vertices up to n. Yep. Okay. With Malta, I start with some inequality. Yeah, so of course I can use this computer software and check it, but we can do also by hand. Let's do it by hand. What's the inequality that I would like to use? I will be calculating on 4 vertex densities because I have 4 here. So I can root on a single edge. And now I would like to write some inequality that will be useful for me. This inequality needs to be equality in the extremal example. And if I pick any edge, and this will be my root, then what I can say, those are exactly here. So if this is x, and this will be of size x. Both going out will be this part, yeah, up to half. So something like half minus x. The things going in the other direction. So it's something here at this interval. Also of x, while those are both going in. Yeah. So I want to write some equality that can be useful for me. So it's tied here. For example, here is x and here is x. So let me try with inequality. This squared and average is a place. It's a true inequality, right? I'm saying just that square of something is positive, and this is nice for me because it's 0 in the extremal example, independently where the rooted edge is. Okay, so now we multiply this. I get this graph with an edge here, and now this is the only choice, right? Because if I put this edge in the other direction, it's the same graph, just rotated vertices. And the coefficient here is 1 because whatever vertex I will choose, I stress that. When I multiply this by this, I get here, but here it's the other way. And I have 2 choices. It can be this way or the other way. And now the coefficient is half because I can choose specific one, but in this square I will have 2, so it cancels out. And squaring this, similar as here. So I get this. I get my inequality. Now I need to do the averaging. What's this graph? This is just a transitive tournament, if you look at it. Yeah, after I forget about labels. So now I need to write here a coefficient, which is probability that if I choose here 2 labels, like 1 and 2, I see exactly this picture. In a transitive tournament, every vertex is different. Yeah, they are in the orders. And I need to choose label 1 in the first one and label 2 in the last one. So I have only 1 choice. Yeah, so it's 1/12. 4 options for the first one, and I need to be here, and 3 options for the other one, it needs to be here. What I have here, if you look at this graph, it contains 4. Yeah, it's here. And there is only 1 tournament of 4 vertices which contains 4. So it doesn't matter how I do these edges here, is this guy. And I need to pick those labels in a specific place. You can just check that this is also exactly 1 placement where I can put them. So it will be also 1/12. The graph here is also a C4. Yeah, it's here. And also there is just a unique choice of roots. Place. And the graph here is what? It's also a C4. It's this way this time. And also there is a unique way to place the labels. Okay. So I obtained the following inequality, which I can write in a different way, just that transitive tournament minus C4 tournament is at least 0. Yeah. This will cancel out, and I multiply everything by 12. Yeah. Okay, and how I can use it? Here. I want to bound density of C4. So once again here, and I'm adding what I have here with coefficient half. So I'm adding half transitive minus half C4. Yeah, this is at least 0 because I just put it. So what I have, half of transitive space, this, and from here I have half of C4. So half plus half more half, and I'm done. I proved exactly what I want. Yeah, so it's a fully valid proof. I don't even need to use Phlegmatic or any software because I guessed what inequality I could use. Yeah, in general, sometimes your problems are small enough and you expect what you should use, then you can just calculate it. Notice that you can write this whole solution by just writing pick an edge, sum up all the vertices which behave like this, subtract those, square it, and use lots of computations, but writing it as sum over all edges and etc. is long, and here it will have clear and nice way of writing it and computing, so it's fast. Let me just put a final remark. If I change this problem into maximizing not 4 cycles, but 4K cycles, then for K at least 3 is open. So if you want to solve some nice conjecture, then you can try to find maximum possible number of 12 cycles or other cycles divisible by 4. And the extremal construction claim to be the same. Okay, thank you very much for today. If you have any questions.